evaluate the limit. Yeah, this is a very interesting limit. It is so interesting that when I tried it for the first time, I thought naively, okay, I can distribute this x to get 12 to the x divided by x minus 1 over x. And then the limit of the sum is the sum of the limits, so I would just simply take x going to 0. And while this is a limit I don't know anything about, I know that this limit diverges to plus or minus infinity. And so I was like, okay, this limit definitely does not exist. But then I look at the choices and they're all constants. So I guess it's not a good way to proceed. Instead, I think it would be very good to focus on this function, 12 to the x, which we don't know how it acts. We don't know how it works. We might have some idea, but we're not quite sure how this function behaves. And by behaves, we mean at this race to the point 0, who wins? Is it 12 to the x? Is it x? That's a very good question to be asking. Specifically, I would like to ask this question for this whole numerator. So this whole numerator is given by 12 to the x minus 1. And now I will use a substitution of 12 to the x minus 1 to be able to get another perspective on the problem. So this is the general theme. You have a limit which you cannot solve because, for example, you have something that looks like this in the limit. Then you just take u to be equal to 1 over x and you have some stuff here, some there, you transform it to some other stuff and then you know what's going on. So that is a general theme to keep in mind. Whenever you have a weird function or a function that you don't know how it behaves, just take the u sub. Good. Now if u is equal to 12 to the x minus 1, then what is x equal to? Well, this is not easy. I'll first write down that u is equal to 12 to the x minus 1. Then u plus 1 is equal to 12 to the x. Yeah, this is simple math so far. But then what do we do next? Tough question. But for these tough times, we need tough functions that will help us solve this. So in that case, when you have something in the exponent which you want to pull down, you can always use the logarithmic function. So I'll apply ln to both sides. I get ln of u plus 1 is equal to ln of 12 to the x. And now notice that we already know that it is a feature of the logarithmic function that we can take this exponent and place it as a coefficient of this ln function, which is precisely what I'll write down now. So these two expressions are equivalent, and that is a defining property of the logarithmic function. Okay, then this is x, and then there's ln of 12. Then finally I can conclude that my x will be equal to ln of u plus 1 divided by ln of 12. Okay, now I am ready, almost ready, to rewrite my own limit. So the first thing we do is we look at this. If x goes to 0, x goes to 0, where does this expression go to? It's very simple. It goes to 12 to the 0 minus 1. 12 to the 0 is 1, and that is also 1. So 1 minus 1 is 0. So we're taking the limit as u tends to 0, effectively. Then, in the numerator, we have 12 to the x minus 1, which is now u. So it's u. And in the denominator, we have x. But I can just write 1 over x. Then, if this is the expression for x, I can get 1 over x by flipping the fraction like this. I hope you don't mind. And that is already a lot of progress with the problem. Next, I hope you do not mind if I bring this ln of 12 outside the limit. The reason I do this is because it's a constant function, or it's just a constant. I don't need to say a constant function. It's just a constant. And this constant does not depend on the limit quantity, right? So no matter if u goes to 0, if u goes to planet Mars, this will still remain as ln of 12. But if u goes to planet Mars, then this expression might change. And that's the key difference. Okay, so now we need to compute this limit, which is still not an easy task. So we will use a trick. And that trick is dividing by 1 or multiplying by 1. So I will multiply by 1 over u, but then I'll divide by 1 over u, because I want to multiply the numerator and the denominator. And you will see you will see how this looks like in a minute. Well, maybe less than a minute, because u cancels out with 1 over u, we get 1. But down below we have ln of u plus 1 times 1 over u. And now notice that all this action is happening inside, so we still haven't taken any limits. So far we're making progress, it's good, but we still need to evaluate the limit. Well, the reason I wrote it in this way is because I want to actually bring this power inside the function. So I want to precisely write this down. 1 over ln of u plus 1 to the power of 1 over u. This is what I want to write down. And then I hope you'll forgive me if I do one more substitution. So I take w to be equal to 1 over u, and then I think everything will be clear. So if w is if w is equal to 1 over u, then if u is going to 0, then 1 over u is going to plus or minus infinity. I don't want to say plug in 0, but plug in 0 there, and this is what you will get effectively. And then this is a limit as w goes to infinity of the following. We had 1 over ln of u plus 1. U is 1 over W, because W is 1 over U. 1 over W, all right, 1 plus 1 over W. And this is 1 over U, so this is just simply W. And now I want to take a moment to ask you if this is familiar to you. Well, right now it does not look familiar because I still have not written it nicely enough. But if you don't see anything that's familiar, I want you to maybe consider this. Does this remind you of anything we've discussed before? Yes, this is actually the exponential number of Euler. So this is actually equal to one over ln of E. So E is defined as the limit as W goes to infinity of 1 over 1 plus 1 over W to the power of W. You can recall the discussion about accumulating 100% over 1 year, or 50% over 2 years, or 33% over, I'm sorry, it was accumulating 100% per year, or 50% per 6 months, or 33% for 4 months. You see where this game is going. So if you go very far off, you get something that looks like 1 plus 1 over W. And if you have it, for example, if you accumulate every 6 months, then you accumulate twice. So if it's 50%, you accumulate twice. 50% is a half. If it's a third, then you accumulate 3 times. Your money accumulates, and so on and so forth. If I do this infinitely many times, I get Euler's constant. This is just a recap of the fact. You can of course refer to the notes if that is not clear. And then in that case, we can evaluate this limit inside by the continuity of ln. The ln function is continuous, and so I can pull the limit inside, so to say. And if I do this, I indeed get ln of E, but ln of E is just 1. So the whole limit is equal to 1. And ln of E is equal to 1 because 1 is the number maybe some color coding would be nice here. ln of E is equal to 1. You can use a calculator to find that out. Or it is simply because 1 is the number which you raise E to get E. So that's what it means. So if this was, for example, x. So this is the general rule. You can also change the coloring, and you will get the correct formula for any expression. Anyway, so this is why it's equal to 1. And there's something that we've been horribly ignoring so far, which is this ln of 12. So I have not written it down in all of the previous expressions, but I can do this now. And by doing this, you will actually get that this limit is not equal to 1. It will be equal to ln of 12, because it's 1 times ln of 12. And that is the trick behind the question. So the trick is to really know how the exponential is defined. The limit as x tends to infinity of 1 plus 1 over w to the power of w, where this is the percentage and this is the number of accumulations you have. Otherwise, if you don't know this fact, I think you'll get an incorrect answer for this exercise, unless you're very lucky and you guess the right answer, of course. In that case, yeah, shout out to you.